Tam şu an yayında. Acaba ne kadar çıkacak?
All right, the next topic is very easy. It's embeddedness. Embeddedness is the, is actually what we had at the top of this ratio. You remember that we had that ratio? So with embeddedness, you look at the number of nodes that you have, connections to both of the nodes that you are interested in. You have this edge, like in this case, for example, Munich and Frankfurt, in this example. So you count all the nodes that are connected to Munich and Frankfurt. This is easy, like Bonn and Berlin. So you count the number of nodes that are connecting both to Bonn and Berlin. So this is embeddedness, right? Okay. All right, so the next question is, because we need to be able to find these two values, like embeddedness and the neighborhood overlap values for all of the edges that we have. So we cannot do this by doing it by hand, counting ourselves. That's not that easy. So we have to be able to do this somehow. It is possible to do it with Cytoscape if you know some more advanced programming. It is possible to write an add-on, a plugin, or app for it. But we want to be able to do it a little more quickly and easily, and that's going to be with a spreadsheet and using sorry, I'm coming back to you in a moment. Yeah, so it will be possible to make it with a spreadsheet. And let's take a look how much we can do without any programming. And from the point that we need some programming, then we will think about it, how to do it. I did it previously for Germany, but now let's do it for France. I think this one is easier. So, although that I made a mistake, and what was the mistake? Do you remember? There was a mistake in here. Anyhow, so what I need to do, these are the edges that I have. This is a weight. I'm not going to use it now. Over here, what I need to have is so what was the, you remember, you have to first remember that what was the formula. First of all, I'm going to be concentrating on the embeddedness, so the top part of this ratio. That's the tricky part. That's not the easy. Well, how can I do it? I'm going to be writing here a number. I will count like between Ancon and Bordeaux. I hope that is Ancon correct?
Ancon.
Ancon. Okay. Not as good as you sounded, but Ancon and Bordeaux.
Bordeaux.
Bordeaux. Ancon and Bordeaux. So I will look at, I have to count all the neighbors of Ancon, like here they are, and also take a look at all the neighbors of Bordeaux, and here they are, and if they are matching, then I have to start to count 1, 2, 3, and 4, okay? So do you know that if we can do it, can you think of a way that we can do it over here like this? And from with the knowledge that you have in Excel or spreadsheet or whatever, not that easy, I tell you. It is, within the scope, it is very difficult. You have to write a program for that. But before doing that, there is a trick. Instead of dealing with this just like that, as this is, you have to, it is much better to use the adjacency matrix. Do you remember the adjacency matrix? You don't. All right. The adjacency matrix was, I was going to have. Yeah, look, I was. All right. Then I have to tell you this again, and that is easy. So how to form an adjacency matrix? First, I need to have a list of all the nodes. In order to have the list of all the nodes, there is a trick. I do this, and here is the list of all the nodes. All right? And I take this. So what I did is I used the pivot table, and immediately it gave me the list of all the nodes. That's very easy because there are lots of repeats here, like there are lots of Ancon, lots of Bordeaux, and many. What is this?
Caen. Caen.
Oh, that's much difficult. Okay, so I have to get rid of all these repetitions. So I do it with pivot table. Here I did it, I copied it, and I'm going to copy that over here. All right, so and I will get rid of the borders. So here they are. And what I was doing also, maybe you remember, copy this over here, paste special, transpose. So if there is, for example, a flight from Ancon to
Bastia. Bastia.
Okay, that city. Then there will be one over here. All right, and the way to do this was several interesting tricks. And in order to do that, I was doing, all right, I'm not going to go in full details of how I am doing it, but I will just do it. And you try to figure out why I'm doing it this way. I have to first do this. Double click, and over here, and I do how I was doing it, I forgot. Let me see, I have to cheat. Here, how I do it. Maybe you know VLOOKUP. So this is, what I'm doing here is I'm looking out for Ancon dash Bastia. Okay? Within this edge list. And if I find it, it will give me the value over there. That is it will return me this text, Ancon dash Bordeaux, for example, Ancon dash Bastia. But it is not there. So what I need to do is to tell me if there is an error or not. If there is an error, it will give me true this time. So what I did is this. I'm looking for Ancon and Bastia, if it is available or not. Ancon, so this gives me Ancon dash Bastia. Looks at this, this, and this. I am looking it up from the list that I have, the edge list that I have. And within this edge list, if I find it, it returns me Ancon dash Bastia. If it cannot find it, it returns me an error. So what I do is I'm catching that error. And what I say, if there is an error, so if that returns true, write 0. If it doesn't return true, then give me 1. So here it is. But if now when I copy this to all this matrix, then I have the adjacency matrix. So if there is an edge between one node and the other node, then it will return 1. If there is no edge, it will give me 0. But in order to do this, I need to first put some dollar signs here. In order to stop this to fade away. So with this one, with A2, I don't want this A to change. And with this C1, I don't want 1 to change. So now it will work. Double click. Oh, it didn't work. I have a backup plan. It didn't work, I don't know why, and it may take some time, especially with this pressure that I have now. So I am going to go back to the one that I did previously. Right, this one. And this one. So, all right. This is the adjacency matrix that oh yeah, of course. Now I understand what I'm saying. I can go back. Good, very good. The mistake that I made was a very stupid mistake. So I want the embeddedness number in here. So it will give me, has to give me, by looking at Ancon and Bastia, for example, it's not going to be looking at, my algorithm shouldn't be looking at Ancon and Ancon. It should look at Ancon and Bastia. So what it will do, I will take a look. If there is a link between Ancon and Bastia, if there is, there isn't. So I will look at the one that there is, Ancon and Bordeaux. There is a link. If I see one, then I will take a look with Ancon and Bordeaux. I will trace all this row, and if I find one in the same column, both of them, then I will count one. Okay, so I will keep that information, and the sum I will put in here into Bordeaux. Let me do it by hand in the first instance. So what I'm doing is this: I'm taking the first row, and I'm looking at the first one that comes up in the columns. Ancon is a 0, Bastia 0, Biarritz 0, Bordeaux is 1. So when I find 1 in Bordeaux, I'm taking Ancon and Bordeaux together, and I look at that 2 rows again. So if I see 1 in Ancon and Bordeaux in 2 rows together, then I'm going to count 1. I have it for Lyon. So that means that Lyon is connecting Ancon and Bordeaux, right? And Marseille.
Marseille.
Marseille. And Nice. And Paris Charles de Gaulle. And Paris Orly, no. Only Paris Charles de Gaulle. And Strasbourg. That's all. So you see, I'm counting all these numbers. Shall I do it again? Is it clear? So what I'm doing is that I'm looking at, my first step in this algorithm should be, I'm looking at the first row, number 1. I take Ancon. I look at the columns. When I find the Bordeaux, I say, okay, Bordeaux is my second node because there is an edge between Ancon and Bordeaux. Then I take Ancon and Bordeaux in here in the row, and I look at them simultaneously together. If I see that both of them has 1, I will start to count. So let me mark this one. So Lyon is 1. Marseille is 2. Nice 3. Charles de Gaulle 4. Strasbourg 5. That's all. So I put over here at 5. The others are going to be 0. But Ancon and Bordeaux is 5. This is the embeddedness number. And it is easy to find the other numbers. But what I do is I make a, if I sum this up, this is going to give me, if I look at Ancon and Bordeaux and, right, okay, let's do it.
That means the embeddedness is exactly the numerator of the neighborhood information, like the one that Ercan was drawing, the intersection of the Venn diagram, right?
Yeah.
So this is the embeddedness.
That is embeddedness, so I'm going to divide it with this number. Let me do it like this. If I go to window and freeze, it's going to make it much more easy. So if I add 5 to 10, that is Bordeaux and Ancon, the total of Bordeaux and Ancon. And what I did is that I summed up the adjacency matrix number. So I have this. So these are the nodes connecting Bordeaux or Ancon. It is 15. So I will come back here and divide this by 15. 5 divided by 15 is my neighborhood overlap. So, but what is interesting for me first to find is 5 and form this matrix with the embeddedness values, because it is more difficult to do, and I want to keep that number, and then I can create another sheet and do this without writing any program. I can do it over here. So, but I'm not going to write it now. I did it before. I used that. I did it for Germany. It's over here. I will share it with you. And this is a very short program that is doing exactly what I said. How to write it is another subject. I don't want to go into that because of time. So I leave it there. But believe me, it works. You can check that. We can copy this and use it for another program of yours. Maybe I can put this in our website, how to do it, a little more detailed. That's going to be better to save time. So when I run that program, I'm going to come up with this. These are the embeddedness numbers. So if there is a 0, then that means it's a bridge. So there is a bridge between Frankfurt and Friedrich. But is it a meaningful bridge? I also have to think about it. I mean, I'm looking at bridges now. Pader's something, Paderborn and Friedrich. Is this a bridge, really, or not? I have to look at the adjacency matrix. Is there a link between Paderborn and Friedrich? No. So it doesn't count as a bridge. Does it? Because first, it has to have a node in between two of them, right? There is no link between Friedrich and Paderborn. But of course the embeddedness number is 0. So what I did is this. I'm looking at, of course, embeddedness number. If it is 0, it gives me the bridges, right? Because that means that there are no shared neighbors. So, but I have to double check, because my algorithm gives 0 for the ones that have no link as well. So what I have to do, adjust my algorithm, not to make this error. That's easy, I can do that. I will do it for you. What can I do? Do you have any idea how can I fix this result? I'm having numbers, embeddedness numbers. The difficulty is that I'm seeing it over here. I'm a little bit excited. I said, oh, Paderborn and Friedrich, there is a bridge. It is 0. But then I go back, look at my adjacency matrix, and I see, well, there is no link between Paderborn and Friedrich. So if there is no link, I cannot talk about a bridge. In order for something to be bridge, there must be a bridge. But there is no link in the first place. So how could it be a bridge? If there is no link, there is no bridge. Right? Think about it. That, over here. Where is it? Here. Yeah. Think about it. I'm talking about like between F and H. F and H. So if I run the algorithm for F and H, it's going to give me 0. but there is no link between F and E. So I cannot talk about an embeddedness number for that. But my way of calculating doesn't recognize that, so I have to fix it. And the best way to fix it is because I'm using 0 for the bridges. What I can do, I can use a negative number for the ones that there are no links. So I'm not going to be falling into this mistake. Is it clear? Or is it too difficult? Right. Okay. I hope it is. So I'm going to give an explanation. I will put the algorithm on the website, so you will see it over there. Okay. I hope that this will make things a little more clear. So I'm almost done with it. I haven't. So at the end, what I will have for each, I haven't done it yet, but you will see that for each edge over here, because now I have this in the form of adjacency matrix. But what it does, of course, I can convert it back to this. So for all these edges, there will be an embeddedness number. There is an embeddedness number that I found. Right? It didn't I? Because what I did was to convert this list into an adjacency matrix. Right? I can do this. I showed it to you how to do it. I converted this list into an adjacency matrix, and this is in the form of adjacency matrix, but this gives the information about the embeddedness. Right? So that means that I have an embeddedness number for each and every edge. I found it. So I can use this information together with other information that I have. I can use it with my strength information. For example, it will be very interesting or very important if I have a bridge or I have a very low number of overlap ratio. But, for example, like think about Bonn and Berlin, it was only Munich connecting them. So the link between Bonn and Berlin looks like very important, isn't it? And if it is it's a different thing. If it is a high value, if there is a high number of flights per week between Bonn and Berlin, or if it's low number of flights between Bonn and Berlin, it's changing its importance. Like I'm looking at this information between Bonn and Berlin. The link between Bonn and Berlin is important because if I cut this link, only Munich will be able to make this link. So if I want to fly from Bonn to Berlin, and the flights are somehow cancelled, what I'm going to do? I have to first go to Munich and then go to Berlin. Right? So that flight is important. That shouldn't be cut.
So is it like a bridge?
Yeah, that's a sort of a bridge. If there was no flights, if it was going to be taking more than, if it was going to take 2 steps for me to go to Berlin, if that flight was gone, let me pull this up. Yeah, Bonn and Berlin. If this link was broken, the only connection I have is through Munich. Of course there are other connections, but those other connections are more than like 2 steps. Right? So that's the reason that I'm not counting them. I'm looking at only the ones that are immediate neighbors. So that means if there was also Munich was not connecting Bonn and Berlin too, then it was going to be a bridge. Now there is only, so then it was going to be zero embeddedness number and zero neighborhood overlap. So then it was going to be a bridge, definitely. Then it means that I have to fly, for example, I don't know, from Bonn to maybe Hamburg, and then to Berlin. You know, that sort of a thing. Sorry, that Hamburg, and then to Saarbrücken, and then to Berlin. So I was not able to go immediately to one city and go to Berlin, but I had to travel 2 more cities and go to Berlin. So
Actually,
then it was going to be very
Also Hamburg, like Munich.
Hamburg and Munich?
Hamburg is also connected with Bonn and Berlin, isn't it? Do I see?
No, it is not. It is connected with Düsseldorf. It goes under. Yeah, that is strange. I didn't know that. So, but what I'm trying to say is this. When I also had this frequency number, weekly flights. I also had weekly flights, you remember, on my spreadsheet. I had the source, I had the target, and there was another number. And that number was the weekly flights. So, I also considered that number as well. And I would be really curious about the number of flights between Bonn and Berlin. Because now it is a crucial flight for me. What is that? Is it a high number or a low number? It is 67. So what 67 means? My highest number is 109. I know that. I did it before. And then I deleted. Anyway. 67 is in the middle somewhere. Right? So it gives me some information. If it was going to be a high number and it is still a bridge, then it shows that it is very sensitive. There's a big traffic over there, but I have only one bridge. So maybe I have to add some more links in order to support that I may come up with. So this embeddedness number or this neighborhood ratio is being used with other information as well. Not only alone itself, it gives me a lot of information, but I can use it together with other information that I have, and we have to think about that. So the last thing that I'm going to talk about is very easy. Very, very easy. I'm going to use this, and it is so easy that all you have to do is to come here, take a graph. This is the Germany undirected. So this is an undirected graph that I specially created. So I go to network analysis and analyze network. This is undirected. I select undirected. Okay, here. Just a minute. I don't want to make a mistake. First, I delete this. This is undirected. Don't look at the arrows and anything. Trust me, this is undirected. So, I will first do this. There is something called betweenness centrality. When you play with this, I will approach this from a different angle. I'm not going to tell you what betweenness centrality is, first of all. I'm going to show you what it is. Not tell you, but show you. So, with the node size you see there are many, many different values about this that you can take. Like I can take, for the node size, I can take the edge count. So the bigger the edge count is going to be a larger node. That's a nice thing. And when it comes to the edge size, I take a look at the available options. There are two options. One is column tree, and that is the, you know, the frequency of flights. So I can make it bigger if there are more flights, narrower, there are less flights. So let me select this. But you see that there is another one that is edge between this. I don't know what it is. I haven't told you yet. But let's select that. It gives me low values to bright colors, like well, green is going to be very low edge between this value, and red is very high edge between this value. And see what happens. Okay, so it's not really nice. The problem is with this. Yeah. And I will change edge opacity to 150. So what do I have now? Of course, I have these thicknesses. It's showing me the frequency. But as you see, there are also these colors. So what these colors do tell me? So it tells me that for example, between, can you see that there is a yellow one over here and there is an almost red one over here? And Innsbruck and Frankfurt is also red. And these two are also red. When I look at Munich and Düsseldorf, is little more higher edge between this value. Düsseldorf and Hamburg lower between this value. Berlin and Düsseldorf very low. And look at the yellow ones. Yellow ones means that they are mid. Frankfurt and Hamburg. So, but what is edge between this? Now I can tell you what it is. So then we can take a look at it again. Edge between this value is this. It's very simple. Take a look at it. Get all the shortest paths and count the number of steps that you go from one to the other. Like, you remember that we had this, let me show you. We have this list. So what I do is this. I have an edge list. This is the list that I have. So what I'm doing is that I'm looking at Berlin and Bonn. From Berlin to Bonn, how many steps it takes for me to go from Berlin and Bonn? Because since it is in the list, it is going to be 1. But there are, of course, ones that are not really linked over here. Like when I look at the adjacency matrix, for example, from Berlin to Bonn, it is 1 steps. But what it is from Berlin to Bremen, how many steps it takes to go from Berlin to Bremen? Maybe 2. Then I write here 2. How many steps it takes from Berlin to Dortmund? Maybe 3. Okay, so I can form a list like that, right? So these are all the shortest paths and the number of steps that I take from one node to the other. All right? Then think about this one. I have all the nodes, like in the adjacency matrix, in the rows and the columns. And I'm taking all the pairs. I take Bonn and Berlin. And from, like, or no, maybe Bonn, Berlin and Bremen. Berlin and Bremen. I take Berlin and Bremen, and I look at the shortest path between Berlin and Bremen. It goes through, I don't know, maybe from Frankfurt. So I write it down. So Berlin and Bremen, and the path to go from Berlin to Bremen is Berlin, Frankfurt, and then Bremen. Okay? So I do this for all of them. For all of them I do it. And then I look at how many number of times I am visiting each edge. So maybe there are some edges more frequently visited. Let me show you this. Now take a look at this one. When you think about all the travels in this network, this is definitely going to be visited a lot, right? Because most of the time, people would like to go from here. For example, all these people who wants to go here would be preferring this path rather than that, the long one. So this is going to be visited more. So the edge between this value is that ratio, that how many times, when you look at all the possible travels, how many times this is going to be visited? How many times people will be passing through this compared to the others? So if it is, for example, 100%, that means that for all the travels, everybody has to pass through here. So it's not really possible for maybe I have 2 nodes. Yeah, this is going to be 100%. Right? So if I have a 3 node, they're all going to be equal between the centrality, 1/3. So because between all these travels, only 1/3 of the time they're going to be visited. But what I can say, I don't know the number yet, but by instinctively I can say, if I'm having travels between these cities and these are the roads, this is going to have very high number. And how about this one? It's going to have a very low number because who wants to travel here in order to go, make a travel in this part of the world? Nobody will take this road. So it's going to be less visited. But if this is going to be, you're trying to come up with which roads will be used a lot, so I have to maintain them more. So this is the value that you would like to take a look. And of course, you would like to take a look as well how many people are traveling, or maybe how many buses are passing through, of course. But this is one of the things that you will be looking at. This road will be needing a lot of maintenance because a lot of people will go through here. And maybe these roads on the top as well, right? Because some of the travels between F and these people over there, maybe. But these guys, no, definitely not. They're not going to be used a lot. Or these as well. Nobody will, in this part of the world, will want to go travel from these roads. Think about it. You want to go from here to here, and you will go all the way here and pass this road? No, this is not going to happen. The shortest path here is this. But who's going to use this road? Only A and D will be using it. Would anybody else be using it? No. Nobody will like to use it. It's too far away. So this is what edge betweenness is. It tells us how many times that edge will be visited, will be passed, will be traversed in order to go from one place to the other. And this is giving me when you look at this kind of the other example I showed you was easy, but when you look at a picture like this, in a network like this, it is not easy to instinctively to come up with something, with an idea that which one is the higher edge between us. You have to have this an algorithm or tool like that in order to paint it. So, is there any peculiarities or is there anything strange for you that when you look at it, this picture?
Can we go back to the previous one? The more toyish one?
The easier.
Yeah. Why don't we ask the question like this? Suppose we have an ant, karınca, and that ant animal, I just put that animal at, say, on node H. Then I'm going to ask her to walk around, travel the node from H to anywhere she likes. And I'm going to tell her that, just do it. Start from now and do it. Today, tomorrow, say, she's going to walk over there a year, more than a year, 10 years, 100 years. All she's going to do is she's going to just walk around the net. Now, here's the first question. Which node over there she visited most? Which node she visited most? A and B. Why do you think that is that way? Exactly, because you're thinking that, I think you're absolutely right, that the nodes that you refer to right now has the highest number of connections. Like, because A has 1, 2, 3, 4, 5 connections, I guess, and so is B. Now, here is the next question. When ant is traversing all over the network, walking around the network, which link she uses most? Okay. So now here is the question. Are the bridges those links that has the highest centrality or highest, not centrality, just strike that out. Are the edges the links who has the highest edge between us? Could you define the bridge? We define the bridge A and B. And the strict definition of the bridge is exactly the overlapping of these two curves, like the point K. The numerator of the thing that we define, structure, n of both D and E. So if that number is 0, then we call this bridge. And now we identify AB as a bridge. And you identify AB as the node that has the highest edge betweenness. Now is my question. Are the bridges the links that has the or have the highest